Okay, so I think, fine.
Yeah. it's
Okay.
fine.
Oh, okay. I see what
Regarding,
you're
yeah, that's how to explain, if he say that, if that question say, the one level below your critical, then that is this one, right?
Yeah.
Yeah,
So that's like I was asking her because I was like, I'm reading this as like the zero, what level below the 0 point energy, and I'm like,
50.
that doesn't make any sense. Like, that's
You say because there
what's
is
lower
no
than
zero.
right. What's lower than the lowest energy? But yeah.
okay, and second question, I think last time I didn't, you just about, ask about the Bessel function or why, when we consider to solve the differential equation is use Bessel differential equation or standard. So I think this before me.
It's kind of like what form you can manipulate
Actually,
the
they are
equation
considered,
into,
yeah.
the differential
So
equation.
you see here, this
Right.
this is general equation, right? For linear equation. The key is this one. This term is trouble. I mean trouble means very difficult.
Right.
So, but if L equal to 0, this term disappears. Then that you can go back to if we can do in general. And then you can see here, if in this term 0, and if potential is constant or 0, then this is just like sinusoidal, I mean the solution,
You're an
right?
artist.
And that one is nothing but this 0th order of spectral Bessel function, is this one.
Okay.
So there are two ways. One, you just set 0, then you just specially solve this one, or just not 0 in general, so we have this solution for Bessel function, and then discuss.
lower than 0 देखो 49 रहेगा
Gotcha.
Is that clear?
Yep.
Okay,
यानी
good.
निकाल्दा 15 निकालेर त्यसलाई 0 lower than 0 यानी निकाल्दा 49 गर्नु पर्यो
Yeah, okay. You explain to him to this one, right? Okay, good. So you done, or you
I'm finishing the last problem.
okay, and the first two not yet?
I don't think I have them with me actually.
Okay, okay.
Yeah.
That, yes, you done?
No,
Now you, okay.
Is it okay if I submit by this
Yeah,
Wednesday?
Wednesday fine, but Wednesday I'm going to maybe assign another homework, so,
Okay.
That's fine. Just
yeah,
कति भयो
yeah, fine.
They said
You
keep it coming.
Keep
Right
it.
back to work.
You just say that you finish, you qualify, then now you have to come back.
For what it's worth,
Okay, got it.
I think quantum went well for all of us.
Yeah.
Oh, that's good.
I mean, only the thermal one I think I screwed up. Others, okay.
Thermal, you mean this
Partition function.
partition function is a gas, right? Did he say the monatomic?
Yeah.
Monotone.
I think I
And
got
you-
a wrong partition function.
Yeah,
so,
you write down the energy. That's classical, right? Not quantum mechanics.
thermodynamics.
So no, thermal. Yeah. In thermal, there are two ways:
Classical
classical,
and
statistical,
quantum.
or quantum. So then your partition function here, whatever you say, yeah, is minus whatever beta. This one. This one depends on quantum and classical. So maybe in your case classical, right? So you need the kinetic energy part, px squared over 2m,
Let's say.
py squared plus a squared, right? And have potential, right? Potential, if like gravitational potential, whatever potential. Then you do the integral. I think that is right. That is integral.
I got stuck there.
D integral dx, dy, dz, and dpx, dpy, dz. And then you do the others. Once you have this, you have this.
I think I got the integral wrong, so I continued the wrong set in the next two parts.
This is not I didn't read this one, but I know this time. Okay, now let's continue our quantum. If you pass quantum, I feel a little bit better that I help you. I'm not sure. But whatever, you pass one, and next time you pass another. Then you're done.
I think the quantum midterm from last semester really prepared us.
Yeah.
10 hours of matrix operations.
Okay, that's
She remembers that
I
question.
Okay, so do exercises. Yeah.
she said, I'm just glad I didn't have to do that week. I didn't have to take that exam over. You didn't have to take any of the exams on Saturday, did you?
No. I have to
It was a
examine next
small
semester.
crowd.
I still think it was very kind that the second question was in matrix form. Just Dirac notation. No intercross.
We start to discuss. If we put this particle into the external field, what will happen? And in this chapter 6, about the spherical coordinates, we always consider the central potential. That means potential has a spherical symmetry. So this is the highest, no orientation dependent, right? And with that highest symmetry, we know that the density is very high. For example, this isotropic harmonic oscillator, we have this only depend on n because energy does not depend on L and M, right? So this is the highest. Another example, hydrogen atom, right? So we have this the genesis n squared for given n, and energy only depend on n, does not depend on L and M. So now we ask ourselves, when we place the system to the external field or switch on the external field, we know usually external field has low symmetry. Like electric field or Mach field is uniform, this just along one direction, right? So that's low symmetry, then the total potential that the particle should be at this central force, central potential plus external. Then if one of them is lower, then this total has low symmetry. So what happened? You will see that the genesis will left, that means energy does not only depend on n, and maybe L and M. So we're going to discuss today. One example is put into the Mach field and the Zeeman effect. So now, this is the topics and the example. Let's consider the effect. What happened? The effect of external field, which is a Mach field. The effect of a magnetic field on a charge. If not charged, we have no interaction, right? Charge. So now let's consider this. All right, so first, now you remind your E and F, right? So if we say there's a Mach field B associated with Mach field, we know if we have external field, must associate with external potential field, right? So for the Mach field, what the potential field looks like? We will have a vector potential, right? So this will give us the associated with this vector potential. then we give a A, right? We use A vector. So, and the relation between this vector potential and the Mach field is that the curl of this vector potential equal to the field, right? That is the relation between these two. Okay, just remind this. And because if this, so we know the Mach field is divergence of this one always 0, right? Okay, so we use this behavior. Now let's consider uniform Mach field. So means this uniform is constant, right? Direction always keep 1, and also any position this magnitude is the same. So, and who knows for this type of Mach field, what is the formula of this vector potential? Who remember? Half of B cross product is R. Remember this? Okay. So, and you can prove that, yes, I leave you to prove yourself because this is just mathematics. I just give you the property though. So this follow this Columbus gauge gauge that diverse of this A is equal to 0. So you can prove yourself. Prove yourself. You prove that if this formula, if you satisfy this. Second one, it is also give this relation, right? So if we select the vector potential is this, the B cross product R half, then you will prove that is B. Again, I just give it, prove it yourself. So that is also very easy, just mathematically, you use the behavior. So, because it's E and M, so we do not spend too much time. But this one, for the uniform Mach field, we know the vector potential is like this. Now we consider the Hamiltonian. That is our quantum mechanics, right? Hamiltonian. Okay, of charged particle. This is also from the EMM. I will not prove that because we know when we have a charged particle put in this Mach field or EMM with electron field and Mach field together, the momentum is rewritten, right? Okay. So assume we still consider mu here. If we like hydrogen atom, right? We have the effective a single particle with this reduced mass. So I still use this one. So now the momentum is like this, minus this term, this the vector potential, right? That is the new momentum, right? Okay. And plus, this is the central potential. Without field, right? Central potential. So that is come from the external, associated with the external potential, right? That is the Hamiltonian for the charged particle placed into the Mach field. And this Mach field is, now we can, these details actually I think we do not need it. We just give you this expression, you prove that this one satisfies this two, so that is 100% this, or associated with the Mach field. Now, we are going to extend this one since now, let's see how to deal with this type system, right? We are going to find the eigenvalue and eigenvector. That means we are going to come back to see here how this degeneracy is lactic. So we expand this one, right? So that is 2 mu, 1 over 2 mu, and inside we have a p square is itself, and then here, because this position may not say since they are operator, right? If I want to write, sorry, yes. If operator, so the position cannot change, so we keep it. So first one is Q over CP inner product A, and the second one Q over CA inner product P, right? Right, two times, and then the last one is this square. Q square C square A square and plus B. If you want to so now we need a step by step to rewrite this one, and you will see the sum physics. Now let's do this too. Because as I said, this since it's an operator, we should be careful. We do not know the P inner product with A is equal to the A inner product with D. That means they commute or not, we do not know, right? So now let's look at this term first. Deal with this one, and then we are going to deal with this. So now, let's look. So P inner product with A, what is P? That's since P has a partial, right? So let's use the arbitrary function to help us. So this product is still operator applied at this state, right? So now this one we know that is minus I h bar within inner product A, right? This is the momentum, right? Linear momentum operator. Then here, since this is a function, this is also a function, so when the gradient do this, we have two terms, right? Okay. So minus I h bar. The first only do this, do I mean this like this divergence, right? With A, and do not add this, and minus I h bar. Get A outside and then, right? That makes sense. Here, this is a vector, right? So this inner product gives us scale, and then whatever it is, you apply this. And the second one is I keep this, so they work on this, and this one is gradient. This is a scale, right? So this gradient is another vector. So I have inner product here. Done. Okay. Now, we're going to apply the property. Yeah, here. This one. So this term is 0, right? Then the remaining is minus I h bar. Okay. And we can change the position here, right? Because this is numbers, this is just vectors. So A inner product is minus I h bar. You agree? And this one is nothing but the linear operator mathematics. So they commute, right? So that means PA inner product, P inner product A equal to A inner product P. Then we come to here. So these two terms can combine together. Otherwise, they cannot, right? Then this, that is this one. Okay. So here, and we write the Hamiltonian again. So now 1 over 2 mu, and the P minus Q over C. Which one we use? I use this one because it commutes. I use A. I use second inner product is P. You may say why you use this one, and you will see, if I use this one, we can derive later. It's easier because this is operator, right? You can put in front. You have to always use some function to help us. So since they are equal, so I can use the second one, right? And then now we come to yeah, the factor 2. I have a 2, right? So, yeah, this is a factor 2 here, right? So this add together a factor 2, so 2 cancel. Ah, okay. Then I separate now. So this 2 mu, we have a 2 to 2 is a mu here, right? So that is second term. Now let's keep the last one. We are going to deal with the last one.
Would that be just the absolute value of a squared, or is it the?
It is be a, yeah, absolute a square, because here this is a, when you do this is inner product, right?
Right.
So that is inner product. Vector, yeah, when we say that, it's always this, right? Because the product only, the scalar product and the cross product, only 2 types. So this is not, yeah. All right. So now let's look at this one. Let's,
Do you need to carry your 2 mu naught over to your last term too, right?
this one?
Yeah.
Yeah, we are going to deal with this one. What's your question?
You still have to carry your 1 over 2
Yes.
mu naught to that, right?
Ah, okay, yes, yeah. You mean this one, right?
Yeah.
Yes, you're right. Yes. Yes, okay, so now let's work on this. This one, that one still, but now we just combine together, but we still want to deal with this, since what does mean this one? Okay. And here, if you know, is this one, right? For the uniform field, this vector potential is half of a B cross R, then inner product P. And now here, the P is on again. So, okay, so I think you agree mathematically, you know this is a cross product with dot product can change the order, right? They're equivalent. So I move this. You agree? What is this? I'm going to moment it. Okay, so that is good, right? That is, make this term now we know physically what is associated. All right, so now let's rewrite the Hamiltonian again, and then we go to the last term. So we have P squared over 2 mu minus, but we have half here, right? So I'm going to give a half Q over 2 mu C B inner product angular momentum, and plus the last term. Then when we deal with here, so we introduce another quantity we call this magnetic dipole moment. So here we define mu L. Here is a vector, right? And actually it's operator since L is operator. We call this as orbital magnetic dipole moment. Here, why we say orbital? Because this operator is orbital operator. Later we are going to use this except to the spin. So if this spin is a spin magnetic dipole moment, if the orbital is orbital magnetic dipole moment, if the J is total, then they are just magnetic dipole moment, right? So from now on, the index is associated here. Okay, so then we write this Hamiltonian again is the kinetic energy part plus minus, right? Minus, okay, minus just B, mu. And now you know this term is interaction between field and magnetic dipole moment, and plus last term. So here we know what happened in magnetic field if the charged particle put in the Mach field, they have its own dipole moment. This one, the field, if field direction is here and the dipole moment is this direction, you try to align. That is interaction, and that is this term. Now we're going to deal with this last term. Okay. Last term, we're going to use, because this is square, right? A is here, that is half of B cross R inner product, another half B cross R. Who familiar with this, how to deal with this, the inner product, two cross products? Just let's try to, because here if we have a it's A here, and C cross B, inner product is E cross M. That's equal to, okay, the first one is C inner product E and multiply the D inner product F and minus D with E, E and C M. Remember this? That's the vector property of product. So we use this now, so we can see here. Now I just, this one will put it right, this is fine. So this is C, D, E, F, right? So in our case, first one is C, E. With R, right? Very good. B squared, R squared. So that is for this one. Then minus, now here D and E. So D is this one and E, right? So that is R, E. And C is a B over R, right? So they are same in the product. Okay, so now we have quarter of B squared, R squared, first term. Absolute value, right? And the minus R dot B squared. Okay. So now let's finally write down the Hamiltonian for the charged particle played into the uniform Mach field. We have the final general expression, then we go to the Heisenberg. Okay. So finally, the Hamiltonian. I'm going to write this way. H naught. Oh, I forgot. I always forgot this one, right? Did I? This is a central potential. So H naught minus B inner product over the interaction with the non-dipole moment. If you can write down this operator, or but at least you know this operator because it's optical angular momentum is operator. And then that one, right? So then it's QA mu C squared E squared R squared minus R dot B squared. Here, H naught is the momentum and kinetic energy operator plus this energy operator. That is without Mach field, right? So we use H naught means if the particle with no any external field, the Hamiltonian is only kinetic energy operator plus potential energy operator. But when we have put it in Mach field, we have another two terms. This one and this one. So that is general. Then we are going to start from here. Now we are going to study the let's see, hydrogen atom. Hydrogen atom in the uniform Mach field. Let's continue this. So we first, there are two ways. If ignore spin. We do not consider spin. Ignore spin. Then this, we call this, the effect is called Zeeman effect. If we consider
I'll talk to you tomorrow sometime. I don't know where
Yeah.
you are.
this abnormal Zeeman effect, anomalous, anomalous Zeeman effect. This one we are going to discuss in chapter 9 because that we need to learn the propagation theory. But the normal Zeeman effect we can then apply right now, since you will see the term Hamiltonian commute with the total angular momentum and velocity. So what is Zeeman effect? This one is let's say energy level is speed into I sublevel. So all the R, so in the 1, 3, 5, not the 2, 4. And then there's a space, the energy level space. Or sub energy level. Level. Space. It's equal. The uniform is the separation always the same space. But here, the energy level split into even number, even sublevel. And the sub-energy space. Depend on the quantum number, which one. So, as I said, we are going to discuss this case because this one we can solve so far in chapter 6. And then we leave this one to chapter 9. All right, so that is we are going to discuss what happened. What is the Zeeman effect? The Zeeman effect is we have this, if you look at the transition line is B equal to 0, you can only see one line. But when B is not equal to 0, if you switch on the Mach field, you will see one, the hydrogen atom, there's one is excitation or transition line, the spectrum. You will see it's split into, in this case, example 3. Right? So that is the Zeeman effect. What happened? And we're going to discuss or explain what happened here. Okay, so now we go back to see this one. This one for any charge. So for hydrogen, the Q is equal to electron, negative charge, right? We just reduce hydrogen two-body system by one single particle with reduced mass, but charge is this one, right? So that is one thing. And then the second one, let's just, this one we are going to rewrite. So in this case, by definition here, right? Oh, I think I have a negative sign. No, that is no negative, but here we have a negative sign. Yes. So in this case, this is a Q over 2mc, but Q is negative, so we have a negative E over 2 mu c L. For this case, right? For this case, then now we can introduce another constant we call, okay, later. So now we're going to discuss, because the mu is reduced mass, right? Is the product of mass, electron and proton divided by the total mass, and is approximately equal to E, right? Because the mass of proton is much, much larger than the mass of electron. So we can approximately, right, this dipole moment of a hydrogen atom as, I'm going to replace mu by me. Okay. And when I write this, so now we can introduce another constant. Let's say here that is minus mu b over h. Here. Yes. So mu b is defined here is E over h bar, E h bar over 2 MEC. We call this Bohr magnitude is a constant, right? So sometimes if you found instead of this one, if you use mu b, that is we replace these numbers by this constant. So now this is one issue, right? So this is the first one issue. Second one, we select b parallel to the z-axis. Then here the b inner product is L is b LZ. That's right? So, okay, now we can rewrite our the third one. We can remove this term. It is here, right? So this, and then I'm going to do third one. So now the Hamiltonian in this case is Hamiltonian is H naught. This is minus, right? But now we have a minus here. So it became plus. Plus mu b over h bar b LZ. Here I already used the information number 1, number 2, right? So that this term, this one I write down here. And the last one, E squared, because negative became plus, right? And now I'm going to replace by mass of electron. B squared, R squared, right? R squared, and this is a B squared, Z squared, right? R is Z, because this inner product R B, so that's Z, right? Then you can see R squared is x squared plus y squared z squared. So this term is b squared x. Now you can take b squared outside, but since we are going to drop this one. So this term has become this, and now we are going to say because the R is 10 to the 10 meter, right? Because atomic radius. So we can drop this one. We are going to drop this related to this term. Terms result with this. So now finally, we are going to deal with is only this term. Now this Hamiltonian not play the role in this of the idea to play into the Mach field, then that can explain what happens in my effect. This contribution, this third term, we just ignore or drop because this contribution is very small, right? And with this, now we can see how to deal with a system if we have additional term above the H naught. That is also the sum of an idea when we deal with the perturbation sharing in chapter 9. We always so when we say perturbation is from here with a perturbation term, right? So now this is one of the case. So how to deal with this? Okay, now how to deal with that? We are going to solve the. This is our goal, right? How to solve this one, right? Now, do not do the details like we do the Heisenberg atom. We have to do the details. Here, we are going to look the commutative relation. If they have some relation commute with some operator which we already know the result, we just immediately use that result because they have a common eigenstates, right? So now, let's first remind you. Do they commute? Hydrogen atom? Yes, right? Hydrogen atom itself without external field, they commute, right? And they have this eigenstates, this radial part and angular part. Now, how about this? Photon. That be H naught plus, I have this plus the second term. So H naught commute is L squared, right? H naught also commute, H squared. Here, yes, we commute. Similar things you consider Z, LZ. Also H naught commute with LZ, and LZ definitely commute itself, right? Right, so that's this. So what's its conclusion? Hamiltonian L squared and LZ mutually commute each other, right? If mutually commute each other, they will have joint eigenstates, right? Or common eigenstates, which is in spherical coordinates, radial part and angle part. We have already have the result, so you don't need solve, right? The eigenstates. So now what's the remaining part that we are going to find a lot of eigenvalue. Okay. So that is the joint eigenstates of Hamiltonian. Then you can see here. And just use this Dirac notation to save time. Right? So this one, I can use Dirac notation. Oh. The quantum number we have n L m, right? So Dirac n L m. I just replace this. So I'm going to right-hand side, left-hand side multiply this bra of these eigenstates. Actually, that is expectation value, right? N L m. That's B by this, the eigen functions B and L m, E and L m. That is energy. That is we are going to find. So that is the way in later when we deal with the system, as some perturbation term. And if we know the zeroth order result, then we just focus on the perturbation by analyze the commutation relation and try to see if we can find this eigenstates, joint eigenstate. Since we are not deal with the chapter 9, but I just give you an idea when we do. Sometimes it is not joint eigenstate, but we can use this as a zeroth order states and then make the correction by similar idea. So now, when it became very easy, right? So we know. So now let's look this one. Okay. This equal to left-hand side, right? Left-hand side is N L M H naught, right? Hamiltonian. There are two terms, right? N L M plus the second term, N L M mu B H bar B L Z. And with this just Dirac notation already enough. So this one we know that E naught, right? And with the index I use here. I know this, right? Hydrogen atom without any field. So I'm going to use the E naught with index n. And then this one and take the constant outside and this. So only LZ. LZ applied states give us, it's an eigenstate of LZ, right? What is the result? H bar M, right? Okay. So we have H bar M or ML, whatever. Yeah, let's use ML since later we have MS, right? If ML, okay, let's use M. Since I use M here. And you know this M is associated L, right? For given L, we have a 2L plus 1 M value. That's all, right? Because then they normalize. So when they apply this, we have this term and then normalize, right? So that is. Okay, so that is the correction energy that we are going to, you see this is cancelled. The zeroth order plus M mu B. And this is sometimes we also introduce so-called Lamarck frequency, that is M H bar omega L. So omega L is defined as E over 2 mu B, 2 mu C, or the mu B H bar mu B, as they call the Lamarck frequency. And you know what is Lamarck frequency? We have a magnetizing moment, so that is rotation with that. About this Mach field, right? There's rotation with that rotation. Associated with this, we have the frequency is like this. Okay. Now you can see here, when we switch on Mach field, in addition to the original high degenerate eigenvalue, then we have additional term. And this term depends on M. These are constant, right? So different M, we have different terms. So now I'm going to say the energy is index N and M, but I'm still going to write down L here because the M implied depend on L. For given L, there are 2L plus 1 M values, right? So this one. Then you can see here, right? So now, let's example here. Example, N equal to 1, L equal to 0, so M equal to 0, right? In this case, 1, 0, 0 is 0. No, and because this term is 0, right? No contribution. That is, okay, let me first get and then N equal to 2, L equal to 0, M equal to 0 again, right? E to 0, 0. Still here. Sorry, it's a 2. But L to 1. So M has 0 and plus minus 1. Then this energy 2, 1, M value. They have 3 different values. 2, 1. Actually just 2 because 0th order only depend on N, right? N plus M H bar omega. So now M is 0 plus minus 1 plus minus 2 and Q plus minus L. How many? 2L plus 1, right? We have 2L plus 1 M value. This number is R, right? R number. That is why we have energy level. Let's consider this case, right? So N equal to 2, L equal to 1. B equal to 0, only one level. But then, when B is not equal to 0, so we have M equal to minus 1, M equal to 0, M equal to plus 1. 3 sublevels. That is effect from here, this term, right? So that is the result. Riemann effect, we can see this, the spectrum is one line, but then we switch on the Mach field, we can see several lines, and that line is due to this effect, the effect between the Mach field and the Mach dipole moment. And that effect split energy only depends on M. since M is odd number, so that should be split in odd number here. Suppose n to 1, L to 0, right? Then you have this is an n equal to 0 case. Then you can see if no field transition is here, only one. But this field we have this transition, right? Okay, so now we can discuss the behavior of this. As I said, that the Zeeman effect has two behavior. The splitting is an odd number, and also the space is always equal space. Okay, so discuss. The first one, difference, delta E, right? The difference between the energy level, that is difference, right? So difference is E, okay. I mean the difference, I think I need to get the index but you can see here, the energy, this one, the same n, right? That if not the same n, that is another story. So for same n, the only difference is m h bar. So only depends this one, right? Sorry, delta m. Because the difference m plus minus its neighbors, right? That is energy level here. Delta E. And this one is another delta E. So the energy level here and is independent of m. That is h bar omega L. So that's why we remove this index. That means this L equal to 1. If L equal to 2, you split into 5 energy sublevel, but the energy space between nearest neighbor, the two energy levels, always these numbers. So that is this one, independent of L. If L equal to 0, there's no, right? Of course, L to 1 and 2, you'll see this difference is always independent. So that is the equal space. That is the answer. The first question about this Zeeman effect. This one, if you substitute this L here, that is just this constant UB. One of the property of Zeeman effect. So the answer why. Second one. I think actually this already answered the question, right? M equal to E and only depend on n. So that is a higher degeneration, but now we are lower by this one because m have 2L plus 1 values, which is odd number. So that's another Zeeman effect. The split is odd number because m is odd number, or because the split only depends on m, does not depend on L explicitly, right? Implicitly, for giving L when m may be 3, if L equal to 1, L equal to 2 may be 5, is 5, right? But that is implicitly implied. But they all are odd number. Number 3, okay, so this the tradition obeys the selection rule. Not -101. So that is the tradition. We know the selection rule, right? The selection, because we put into Mach field, we have see this between the states, initial state, final states, and this integral of this dipole moment. And that dipole moment has the symmetry. So when you apply to the initial final states, you will see sum of integral is 0. That's due to symmetry. So non-zero term is satisfied by this. If the m, delta m is -1, 0, and 1. The number 4, I just mentioned, I think I already mentioned here. So you can see this, the Zeeman effect, or normal Zeeman effect, not totally release this the degeneracy, just partially, right? Partial release the degeneracy. Because it only given M, but L still not. Example here, for example, energy, let's consider E200 equal to 210. You see here. So when N equal to 2, but L equal to 0, this term always 0, right? So then, even though placed into Mach field, if the L is 1, but M equals 0, they have no split, no any difference energy. Another case is E3, right? E3, 0, 0, 3, 1, 0, 3, 2, 0. If M, you see here, even though L is not same, but M same, they still keep the degeneracy there. So that means this normal Zeeman effect cannot completely release all the degeneracy. Still have a partially degenerate. For same M, same N, but different L, they still have the same energy level. Another example, 3, 1, 1, and E3, 2, 1. Right? L not same, but M same, so the energy is the same. Okay, I think that is the simple, or just brief discuss the effect of the Mach field, how the effect will lower or left the degeneracy. Now we go to chapter 7. Chapter 7. So far, from the last semester, we introduce or discuss the one dimension. Chapter 4, we discuss the one dimension system, right? Chapter 5 is the orbital. Angular momentum. And chapter 6, fluidity form, right? Now we go to more detailed discussion, think about the rotation. So now, chapter 7 is about the rotation. The rotation means, okay, we have states. So we know state rotation operator, right? So after this rotation here, that is an operator applied to this, you go to new state, right? Operator, after the rotation, will go to the new operator. So now we are going to ask what happened. What happened after the rotation? Those the question we ask ourselves, since we already know the system, right? So now we are going to see the state of the system. What happens when you perform the rotation over the operator? That is first question. And then what is the operator, a rotation operator? Rotation, we have not discussed this particular operator, right? Operators. What is the fit operator? Properties. And you will see that rotation is not independent with any arbitrary operator. Actually, this rotation is direct connected to the angular moment or angular momentum operator, spin operator. Like you learn this classical mechanics, we know any operation is associated with a generator, right? That generator in this case is angular momentum. So, and then we are going to discuss with such rotation, what kind of physical quantities conserved, or which are the commute together, and what kind of properties of system under the rotation. So that is the chapter 7 we are going to answer, and then at the end, addition of angular momentum. We so far just in chapter 5 we discuss each individual angular momentum operator. Momentum. How about if we have two operator angular momentum operators? If they are equal to, or what kind of properties? That is more important. I remember one time you asked TG coefficient, right? That is, yeah. So we have, for this case, there are two types of the joint eigenstates. And depending on which one from this one to switch to another one, there's a CG coefficient. So those discussion is the second part of this chapter. Now let's first consider what happens if the states and operator under the rotation, right? The first section about the classical, I just skip that because I think that you're familiar with. And we just direct to the section 2, the rotation in quantum mechanics. Consider rotation in quantum mechanics. This the question here. So now, this states, now I'm going to introduce R or rotation operator, and later we're going to find how to express this one to these new states, right? So that is we're going to answer our question, how this states and operator so here, this R in the expression we define, this operator is, suppose we have an arbitrary vector A, and then this means is rotate about this axis with angle phi. That is, we call this is a rotation, right? Okay, so now we are going to see how to determine the states and operator and after the rotation. So now see this define the operator is that if we have the new states psi prime cap after rotation, right? So that is this effect acting, the rotation operator acting on the initial states, right? That is definition. So now we are going to know if we define this is the operator. Then let's see this one, the behavior of this operator first. So the inner product of the states, right, should be equal to here. If I write down this one, and I hope you remember this. This part, or you take the graph separate, means take this complex conjugate, right? I mean the diagram, this chapter 2, remember? And then when we say that, when we take this as Conjugate operator means if a cat became brown, if operator became its conjugate, right? So that is. So that is just to remind you. So that's why here, this one, I write down here. That's the dagger, because follow this, right? So now we know the rotation will not change this magnitude of this the state, only change the orientation, right? So that's B equal to itself. That is the rotation behavior. If a change in magnitude, then that is not only rotation, but at least some others. So, you know, that means this rotation operator dagger multiply itself is equal to identity operator, right? And then because, so if I immediately write down this, will agree. If inverse equal to the dagger, because this one's inverse multiply self always equal to it, right? But now this is a dagger multiply. So what kind of operator if we have this behavior? Chapter 2? Unitary. Yes. So that means the rotation operator is a unitary operator. That's important. Okay. Then this is let me see. Yeah. That's the first one. Then we can see in the position representation. Representation. The states cat project to the position representation means this one, right? And that is wave function, right? Remember this? Okay. In the position representation, right? We use wave function, and that is nothing but the cat project to the eigen or basis vector of this position representation, which basis vector is all this. This is the basis vector, right? Build up this position in the representation. So, okay. So now let's look at this one. I'm going to find psi prime, which is after rotation. How to find, because this is a relation here in arbitrary or direct notation. Now we are going to find in the position representation, since we always when we deal with the details, we have either position representation or matrix representation, right? So now let's consider here. So that is here, right? So that is R. And this is a rotation operator, because psi prime is here, right? Is this one defined? Okay, now let me write down here if you agree. So now, so this part now I write down. That means here, this is operator outside of bra. Now I put inside bra, so they are equivalent. Now again, just remember this, because here, right? So let's consider this. R dagger, apply this R. Take this. Complex conjugate, okay, not just this. This one. This is a vector, cat, right? This cat is R, the rotation operator applies R, I give a new vector. You can say, consider it R prime. Right? Okay. But yeah. No, let's look this one. It's a dagger, not itself. But this is another vector, right? Cat. So now let's look this. It's a dagger. It's conjugate. So now here you will see here. Okay, that's good. You agree here, right? So that's just like something here, right? Then this is inside, so I take outside. Right? Like here, right? Like this one. But this one is not diagonal. Here I have diagonal, so I have to take the diagonal and the diagonal, right? So that is this part, this one. So this is the operator Rn angle phi applied to the bra. That's equivalent. I move into this bra, which is Rn diagram. That I use this relation, right? So now, what does mean this one? This is a cap, and project to the position representation. If you project to R, that is set R, right? But now it's project to another R, we say R prime. Then this R prime actually is yeah. Okay. If I agree, I use parentheses. If I say this is R prime, you agree? You can accept, right? If this is R prime, so you know this you accept, right? The cat project to R, we give a function as function R. Now I have a set project to another R prime, that's be function R prime, right? But this R prime is nothing but with rotation, the R dagger act on the R. So what does means? Now I'm going to summarize. So then this in the position representation, yeah, this one. This is arbitrary, right? The cat, in terms of cat. But now in the position representation, this one is this. This operator, this one is this. But that means now the operator inside to this, the variable instead of function. That is different. Some key. That means I rotate this function, actually I rotate the operator, the variable itself, not function. Or you just, you look the function, how the rotation operator apply, is a rotation applied function, but actually it is rotate. R dagger, rotate is the vector, like the rotation passive and active. So suppose now this R, if you're familiar with this classically, now R in this case replace this one because this is a function, and this are basis. That makes sense? Okay. So you consider, you compare with this one, that R here is xy, that's basis vector. Build up this space, right? And this one, any vector in the space R is a kind of function here. So you can either rotate, you may apply the R. This R is not this R, right? Be careful. So if you apply this function here, that means you rotate with a certain angle here. That is actually, that if the operator rotation is counterclockwise, then the R dagger is opposite, right? So something like you rotate with the basis vector. This is a passive rotation. This is active. In this classical mechanics, we also discuss this a little bit at the moment. So that is how, that means we are interested in how this rotation operator applies the states. In this case, this one, that is active, but equivalent to keep this function here, but rotate it to the basis with the opposite angle, because it's R dagger, R in dagger, right? So that is the story here. That means when we deal with this wave function, see how this rotation operator apply or effect on states, that's just equivalent to rotate the operator at the basis or the variable by opposite direction. Okay, let me keep here, and we keep continuing on Wednesday.
talked about this in classical?
Yeah.
I'm trying to.
Chapter 8, or
Yeah.
we introduced this infinitesimal infinitesimal is transformation, and one of transformations is rotation.
Yeah.
So from A to B, remember that? Yeah, that's
Okay.
we have this something like a passive or active, but usually we prefer passive because then we just deal with this basis vector. And not function itself. If function, you have to consider sine function is rotate, become cosine, sine plus cosine, that becomes. But if x to x prime, then they can have this relation. Just replace x by x prime. Yeah. Okay.
इमर्जेन्सीको लागि फोन लाग्छ एउटा त लागि हुन्छ
Are those all your exams?
What?
Are those all your exams?
No, these are things I have to grade actually. I have to write the exam. There was an exam to do. Yeah.
When do you have to get that back?
Friday?
Friday?
Yeah. This is actually half of it. Like we might just the other half then stuff.
I mean, that looks like so much fun. I wish I had enough time to help you.
The good thing is
Please do it.
But I'm busy, I'm sorry.
No, you're necessary. You promise. Help him.
the good thing is this is there's no weekly stuff like only 3 like
Okay.
one exam, another exam in a month.
I did the exams last semester, and I didn't like that portion of it. I would rather have just 1 hour or 2 hours a week.
Okay.
I'd rather be in the classroom any day of the week instead of just having a mailbox flooded with papers.
Yeah, that's not
Don't you usually
Yes.
like